Greetings everyone, welcome back to college algebra, and it's time to talk about the different types of polynomial division. I want to show you three different methods that are employed anywhere, everywhere, by different people all over the place to do polynomial division. And at the end we'll talk about the one that I'll be using the most in the next few sections to talk about the analysis of polynomial functions. We're going to analyze, through this whole unit, we're going to analyze polynomial functions of higher degrees, things with x cubes, x fourth, x fifth, things like that. Learn how to graph them, how to factor them out, and things like that. And where we start is with polynomial division. I know, sounds kind of, disconnected there, but you'll see. So, I want to show you three different methods. This scene is method number one. Okay? So to do division first, let's get a couple of quick little examples of multiplication. I know you've probably done tons of it, but let's practice. So what I have right here is a multiplication with a remainder. Okay, this is how remainders are written with what we call the remainder theorem. I rewrite something as a multiplication, and then it's the leftover 20, right? So later on, when I redo the division from this, you'll see that we'll get a remainder of 20. So let's multiply out here. I've got the 2x that I'm going to distribute. That's going to give me 6x squared, cubed, x times x squared is x cubed. And then 2x times 8x is 16x squared, and 2x times negative 5 is minus 10x. Next, I have 21x squared, and I have 56x, and I have minus 35, and I still have the plus 20 in there, right? So let's sum it all up, and this is going to be equal to 6x cubed plus 37x squared plus 46x minus 15, right? So good old multiplication there. And then let's do the same thing here real quick and get these two out the way. So I've got 6x squared times all three of these. So that's going to give me 6x to the fourth. That's going to give me 54 x to the 3, and then minus 24 x squared. And then 1 gets distributed here, so 1 times everything just gives me plus x squared plus 9x minus 4. I'm going to add all that up, and it'll give me 6x to the fourth plus 54x cubed minus 23x squared plus 9x minus 4. All right, so now what I want to do is I just want to show you how, we're going to take these multiplications and we're going to reverse them, okay? So polynomial division, the first method is the one that you're probably the most used to, and that is long division, okay? So long division is when I take something like 6x cubed plus 37x squared plus 46x minus 15, and I'm dividing by, say, something like 2x plus 7, right? So I'm reversing this multiplication here. I'm going to do this division, long division. So just like you would with a normal long division with numbers, right? If I were to do something like 16 divided by 5, right? The long division for this, I would write like this, right? No different here. I would do exactly the same thing here. I'm going to write the 2x plus 7 and divide it into the 6x to the 3 plus 37x squared plus 46x minus 15. right? So it should look just like what you're accustomed to. And the pattern for this is going to be very similar also. But one little side note, make sure in your division that you have every power of x accounted for starting at the top. And this is important, just like in long division here, it's important to have all of the numbers in the different place values and have all the columns there so that I can line everything up when I'm doing my subtractions. Okay? So it's the same idea with the normal long division. Let's get this out of the way now. Okay, so I'm going to make sure I have all my powers, right? 3, 2, 1, none. Make sure that you can count from the highest power down to the none. Okay, and if you skip 1 or 2 or whatever, then you need to put zeros in there. Okay, and the same thing goes out here. 1 and none, okay, that's got all the powers. An example for you that doesn't is like this one. You see how it goes from 2 to none? We skipped the 1 in there, right? So I would have to put a 0x to the 1 in the place of this. And we'll do that in a minute. I'll reiterate this. Just make sure that you've accounted for all of the columns, because I need all of those things to accommodate the structure of the division, okay? And actually all of the methods are going to have one way of driving that same point in one way or another. Okay, so how do I do this long division? First, we look at what can I multiply to match this front, okay? So here's what I need to do. I need to pick something that I'm going to put here. And whatever this something is, when I multiply by 2x, I match the 6x cubed. And the reason I want to match it is because I'm eventually going to subtract, and I want to completely zero out the column, okay? That's how you do the polynomial division. We're going to slowly, one column at a time, zero them out so that I can eliminate, 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 and then just see what's left at the very end. All right? So here, I'm going to say what times 2x will give me 6x to the 3? That would be 3x squared. Because 3 times 2 is 6, and 2x's plus 1x is 3x's. So that's my first entry of the answer, right? However, to continue in the division, what I need to do is, just like with your normal long division, you start with whatever your answer piece is, and you multiply by the whole divisor over here, and then you subtract it from the dividend here. Okay, so next what I'm going to do is I'm going to multiply 3x squared times the 2x plus 7. The front one should match. That's by design, right? We did that on purpose. Then 3x squared times 7 is 21x squared. All right, now that you've gotten to this point, we need to subtract. Remember, that's what division does. It subtracts things over and over and over again until you've wiped out all the columns. Okay, well, when I subtract something that has multiple terms, don't forget you have to distribute the subtraction. So this becomes a negative 6x cubed, and this becomes a negative 21x squared because I'm subtracting. The front guy should wipe out, like so. And then I've got 37 minus 21 in the x squared column. So that's going to give me 16x squared. And then the rest follows. Plus 46x minus 15. All right. From here, I start over again. What can I multiply by 2x so that I match, right? I want this to match up. So what times 2 is 16, and how many x's do I need, right? So 8 times 2 is 16, and x times x is x squared. I'm going to keep this positive because that matches the 16. And then, just like before, I multiplied that 8x times all of this out here. That gives me 16x squared and plus 56x. right? Because 8 times a 7 there. Now, just like before, I have to subtract. So I'm going to distribute. This becomes a subtraction. This becomes a subtraction. I just change the signs, really. If this were negative, I would have changed it to a positive, okay? But it was already positive, so I just changed it all to negative. The front guy should eliminate. We design it to do that every time. You should be wiping out whole columns at the front. Now, what's left? 46 minus 56 is negative 10x. And then this is still here, minus 15. All right, then start over again, right? What number or what term times 2x is going to match negative 10x? Well, that's going to be minus 5. Minus 5, negative 5, times 2x is going to give me the negative 10x here. Right? It matches. And then negative 5 times 7 is negative 35. All right. I got to subtract. But here to subtract, I'm going to change both of these signs. Because look, technically what I'm doing is this. I'm putting a negative on this whole thing. That's what I'm technically doing when I'm subtracting here. But instead of, writing out all of the steps and getting them in the way, I'm just going to change these signs. Right? They were negative. Now they're positive. That's how you subtract with polynomials. You just change a sign on something. The front guys should wipe out. They do. And then if anything is left over, that's your remainder. How do I know that? Because my front guy here has an x, and now the leftover bit over here has less than that. There is nothing I can multiply by the x that would give me something that doesn't have x's. Okay? So that's how I know I'm done, because the highest power of what's left over is lower than the highest power of what I'm dividing by. Okay? See, right here, I knew I could still do one more step because x and x match. But here, this is less. Okay? If out here in this divisor I had x to the 5th, then as soon as I hit x to the 4th in the leftover, I'm done. Okay, I can't go any lower than what the highest power over here is. So, how do I rewrite the answer? Well, it's whatever's in the numerator, whatever's above the division symbol up there, the long division bar, and then I have to add in my remainder. So this division, I would say, equals 3x squared plus 8x minus 5 plus, now I have a remainder. I can't just say plus 20, that doesn't make sense. It's like a mixed fraction. I have a whole number part, and I've got 20 over 2x plus 7. Do you see how I just put that over the original thing that I'm dividing by? Yeah? Okay, now the next thing I want you to notice that's going to help us with some understanding later is that this statement right here is the same statement as this being equal to this, right? Look really closely. If I multiply by 2x plus 7, right, then this statement here becomes this, because the 2x plus 7s would wipe out over there, and it would be equal to this. So really, the division statement is just another way of rewriting a multiplication statement with the remainder. But when you're doing a division, this is how you're going to want to write your answers. The whole number part, the whole terms part, plus if there's a remainder, that needs to go over the original divisor. Okay? Let's do it again. Let's do it with this one right here. Let's do 6x to the 4th plus 54 x cubed minus 23x squared plus 9x minus 4 divided by 6x squared plus 1. Okay? Let's do this. So So then you should be thinking, oh, well, let's just set it up in the long division again. Yes, let's do that, right? Let me make a little bit more space than what I've given myself here. I'm going to zigzag here. That'll work. So then what I have is 6x squared plus 1 into 6x to the 4th plus 54x cubed minus 23x squared plus 9x minus 4. Okay, now remember, before you begin, I have to make sure that I have all of the necessary columns. All right, well, let's see. I've got 4, 3, 2, 1, none. Good. 2, none. Uh-oh, we're missing 1. So instead of 6x squared plus 1 here, I really need to write this as 6x squared plus 0x plus 1. Okay? That's going to make sure everything lines up when I do all of my multiplications and listing it out and combining all the columns. Okay? And the same thing would go with the inside. If it missed any powers, you need to put a 0 with that power in there. Okay? So now, same idea. What can I multiply by 6 to get 6? That would be 1. And how many x's do I need to go from 2 to 4? That would be 2, right? So x squared. X squared times 6x squared would give me 6x to the 4th. X squared times 0x would be 0x to the 3rd, because 1 times 0 is 0. And x squared times 1 would be x squared, like this. All right, now don't forget, we have to subtract. So all of these are going to change sign. Minus, minus, minus. Right? Okay. So then the front column is gone. This one is gone. And I'm left with 54x cubed minus 23, negative 23 minus 1 is negative 24x squared. And then I bring the rest down, right? I got all of this. Plus 9x minus 4. All right? Next, I need to figure out what times 6 will match the 54, and then how many x's do I need? So 9 times 6 is 54, so I know I'm going to have a 9. And I need 3 x's. I've got 2, so I need to do 1 more x. 9x times 6x squared is the 54x cubed, as it should be. 9 times 0, I have 0x squared, because x times x. And 9x times 1 is 9x. Okay, now remember, we're subtracting, right? So here I go. Subtract, subtract, subtract. Because they're all positive, I can just change them to a negative, and that means subtraction. Vice versa, right? If you have a negative, you switch them to positive, and that's subtraction. Front guy should go away. He does. I'm left with negative 24x squared. 9 minus 9, I have 0x here. And then my minus 4 is still there. All right. Well, we're almost there, right? This is x squared and this is x squared, so I know I can go one more time because they match. The leftover isn't lower than what I'm dividing by, so I can still keep going. What times 6 will give me negative 24? That would be negative 4. Negative 4 times 6 is negative 24, x squared. Negative 4 times 0, right, 0x. And negative 4 times 1 is negative 4. I'm going to subtract. Remember, what that means is I change the sign. So positive, technically this was already minus, so I'm changing him to positive and positive. Notice this zeroes out. This was already 0, and negative 4 plus 4 is 0. So I actually do not have a remainder here. Okay? So notice, what does that mean? What's my answer? This division equals x squared plus 9x minus 4. Okay? And notice that makes sense, right? Because if I actually multiply 6x squared plus 1 times x squared plus 9x minus 4, well, that's what we did over here, right? If I multiply those, I get the thing that I was dividing, right? So this should be the way this division works out. This is how you set up long division, okay? Again, let me stress, just make sure that you don't miss any columns when you're lining these things up, okay? This is definitely the oldest of the old school methods. It is a lot of writing of the letters and things like that, and it does lack, some of the fun that comes with doing some of these things. But it is very tried and true. It will always work if you practice and do it the correct way. There are no restrictions on this type of division, so that is sort of its advantage here. This second method that I want to show you is sort of an alternative to the long division. This method is still not one that I'll use a lot in a lot of our other things, and that's because I don't need something this powerful with a lot of the divisions that we do later, and you'll see why in a minute. But this is a good alternative to the long division that we were just doing because it is usable everywhere just like it was. It is more concise. It doesn't take up as much space. Long divisions can grow and grow and grow. This method is going to just pick some space and stick to it. And it's, with a little bit of practice, it can be very intuitive. Okay? It's going to feel a little weird at first. Before we get to the division, I want to do a multiplication by the same method. Okay, so if you've seen this before, then you'll know exactly what I'm doing as soon as I draw the picture here. Okay, but basically what I'm doing here is I'm multiplying and dividing by what we call tile method, or tiles, or charts, or grids, or whatever we call it. But usually I call it a tile method. Okay, so the official title is multiplying and dividing by areas. Okay, because rectangles length times width is an area, so on and so on. So watch, I'm going to multiply this polynomial multiplication using what we call tiles or area method. Okay? So here, I notice that I have 3 pieces and 3 pieces. So if I'm going to multiply, I just need to set that up appropriately, like this. I'm going to make 3 rows. And now I'm going to make 4 columns. And the reason why I need 4 columns, I know we only have 3 objects here. I'm going to list the objects on the side from the first guy. Okay? X squared, 3x, and negative 7. And then along the top, I need all of the possible spots. Just like with the division, I don't want to skip a spot. So here I have 4x cubed. I've got 0x squared, I've got minus x, and I've got plus 2. Okay? Multiplying by the area method just means I'm going to do the length times the width on each one of these squares. Okay? So for this square, I'll do 3x times 4x cubed. And over here, I'll do negative 7 times 2. And then when I'm done doing all of those, the total area is the complete multiplication of both polynomials. And what you'll notice is, since I have everything lined up correctly, the diagonals are going to be like terms. And that's the way we want it. Okay, so here I go. First multiplication, I have 4x cubed times x squared is going to be 4x to the 5th. Then 0 times 1 is 0x to the 4th. Negative 1 times 1, negative x to the 3. And then 2 times x squared is 2x squared. 4x cubed times 3x, 12x to the 4. 0x3, negative 3x2, and 6x, right? 2 times 3x. Here I have negative 7 times 4x cubed, negative 28x cubed. Times 0 will be 0x squared. Negative times negative is positive 7x. And 2 times negative 7 is negative 14. All right. Seems like a lot more work there, but if you think about it, I haven't done anything that I wouldn't have done already if I were doing the FOIL method or the distributive property method. Okay? This is just more organized, a little bit more writing because of the grid. But here's the thing. Your like terms are always going to be in diagonals. So this is going to be a term. 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 And technically this is a diagonal of one term, and so is this one, right? That's going to be a term. So I ran out of space on my side over here, but typically what happens is I like to draw it out to the side, and then everything lines up here, okay? So this first guy here is just 4x to the 5th. And then next I have 0 plus 12. Notice they're both x to the 4th. So that's going to be plus 12x to the 4. Then this diagonal here, I've got negative 1, 0, negative 28 is minus 29x to the 3. Then 2 minus 3 plus 0, negative 1x squared. 6 plus 7 is 13x, and minus 14, right? I know everything got skewed when I did these things, so this diagonal went here, this diagonal went here, this diagonal went here. Usually they don't do this. Usually I'm able to, I didn't give myself enough space on the side of the board there. But this is the multiplication answer, okay? It's not actually any more work than you would have done in any other method. The only extra writing was setting up the grid, right? Writing the actual lines. But if you're the type of person that likes to see that kind of organization, then this is the perfect method for you, right? You're not going to miss any of the terms. Just make sure that you have all of your powers accounted for. And then the diagonals will add up to give you your finished product, literally product, right? Okay, so we can multiply by area method. Division by area method is just like this in reverse with a little bit of solving involved. Not actual equation solving, I mean, but notice the multiplication answer, the product, right? The large total is the result of the diagonals. So what I have to do in a division is set up one of the sides that I'm dividing by, and then the top, the thing that I'm dividing by, is going to be what used to be the answers from the diagonals. And so I'll have to work backwards to repopulate the grid, and then that will fill out the top for me, and the top will give me the answer to the division, okay? So I've got these same two divisions that we did a moment ago, and I want to demonstrate to you how I can use the area method to divide those and get the same answers in either the same amount of work or less than what we were doing before. Okay? So, right here, I've got, I'm dividing by 2x plus 7. So right away, I know that my chart is only going to be 2 rows tall. Okay, so I'm going to start my chart off like this with only 2 rows, and that's because I know that I have a 2x and a 7 on the side, right? That's my thing that I was multiplying by. Now I'm going to need to fill out how many columns I have, so I look at this. I notice that it's x to the 3 and x to the 1. 3 minus 1 is x squared, okay? So I know that this first row in the answer is going to be something x squared. I don't know what yet, and I don't care, but I know that since that's got to be x squared because of the 3 minus 1, I know that I could also have something with an x, and I could have something as a number, okay? And then I also leave one more spot for a remainder. Okay, so I know that I've got this at least. Technically, at this point, like we didn't do remainders over here. I only actually need the 3 columns, but I always leave a little spot open for remainders over here, okay? As you know a minute ago, we do know that this one does have a remainder, but you wouldn't know that to begin with, okay? So I'm going to set this up, and I'm going to leave a remainder column over there just in case I need it. All right, so I'm almost ready to start dividing. I need to remember that my diagonals, right, that's these things right here. This diagonal, this is a diagonal, this is a diagonal right here, and technically this is a diagonal with the remainder value right here too, okay? So my diagonals need to be the things that I'm getting from the numerator here, from the thing that is the total. So I've got 6x to the 3. I've got 37x squared. I've got 46x. And I've got negative 15. Right? Those are going to be the sums, the totals of my diagonals. Remember, the diagonals add up to as like terms to the answer part here. So if I'm reversing, this has to be the sum of this diagonal. Now wait a minute, this diagonal is only 1 square. Yes, that means what? That means I can fill out this directly. This has to be 6x cubed, right? And then that's what starts the dominoes knocking over here. Look, what times 2x gives me 6x cubed? I can answer that question, right? I can go this way to this way and get my actual answer here, right? What times 2 is 6? That would be 3. 1x from 3x's is 2x's. And it's exactly the 3x squared. I was expecting x squared, wasn't I? All right. Now, to continue, I need to finish filling out the chart. Well, I can do that with multiplication. What's 3x squared times 7? That is 21x squared, right? Okay. But this diagonal is supposed to add up to 37x squared. So, what over here could I put plus 21 to get me 37? That's what you need to be asking yourself right here. Right here, what plus 21 equals 37? Right? What number plus 21 would give me 37? Or if you want, you can think of it like a subtraction. This is the total. 37 minus 21 gives me what left over here. Okay? You would say 16x squared, because these are the x squared diagonals, right? Okay, well, I got that top guy again, right? What times 2x would give me 16x squared? Right? That would be 8x. Okay, but now that I have this top guy, I can finish filling out the column. 8x times 7 is 56x. Right? Okay. Keep on going. 46x is the total of the diagonal. So 46 minus 56 is negative 10x. Right? All right. So then what times 2 gives me the negative 10? That would be negative 5. Now that I have this top piece, I can finish filling out the column. Negative 5 times 7 is negative 35. And this number only had the one number in its diagonal, but it doesn't match, right? This number should go here, because remember, look, the one number goes here. This is when the division hits the need for the remainder, okay? So right here, I'll do the negative 15 minus negative 35. Like that. What does that give me? 20. So, My answer is all along the top here. And I have remainder 20 as expected, right? So the answer to the division is 3x squared plus 8x minus 5 plus 20 over the original divisor, 2x plus 7. Right? The answer we expected to get. It's the actual answer. Okay? So this method right here has the same amount of work as the long division. It's just organized differently. And if it makes sense to you, then this is definitely the way you'd want to go, because this is more organized, in my opinion, than the long division. Let's do it one more time for this guy over here. Okay, so I'm noticing in the denominator that I have 6x squared plus 1. Now remember, I have to remind myself, wait a minute, I'm missing a power. So I know that when I set up my chart over here, right? I know that when I'm setting up my chart, I'm going to need 3 rows. Because I'm going to need a 6x squared, I'm going to need a 0x, and I'm going to need a 1. Right? Okay. Next, 4 minus 2. I should be expecting an x squared here in this front guy right here. I don't know what kind of x squared, but I know that the leader's going to be x squared because of the relationship between the two leaders here. So that means I'll also need an x, a number, and a remainder. So I'll have my columns for each of those. Okay? And I'll just leave this kind of hanging out over here for remainder. All right. Let's go through that process. I need my diagonals in order to do that, right? I need my diagonals in order to fix this up. So this first diagonal right here, I'll start way over here, was 6x to the 4th. The next diagonal goes through both of those two, right here and here, is 54x to the 3. Next diagonal is these 3 blocks, and that should add up to negative 23x squared. Okay. Next, this diagonal right here should be 9x, and yes, that does count the top block of the remainder. It doesn't have to, but it can. And then this guy right here should be the negative 4. Okay. So let's go through and fill out the different spots here, right? Well, I know from this top diagonal, this is always the way that it's going to start, right? It only has 1 block. So 6x to the 4th, right? Then you have to ask yourself, what times 6x squared gives me 6x to the 4th? Well, 6 times 1 is 6, right? And then I have 2, I got to get the 4. So it's got to be just x squared. Well, remember, now that I've got the top piece, I can fill out an entire column. That's what you should do. So x squared times 0x is, whoops, x squared times 0x is 0x squared, and x squared times 1 is x squared. Okay? Then move on to the next diagonal. Don't skip any diagonals, okay? We finished this diagonal. I'm done with this one. Next diagonal is 54, and I've got a 0 waiting. Well, what does that mean? Well, 54 take away 0 is still 54, and it's x squared, right? Because that's the, x cubed. Whoops, I made a boo-boo one here and here. I hope y'all caught me on that one before I messed you up too bad. Okay? X cubed diagonal. Apologize. All right, so I've finished, got back up to the top up here. So keep going, right? What times 6 is 54? That would be 9. And then from 2 to 3 is a single x, like so. All right. Now I can fill out the rest of the column because I know the top. 9 times 0 is 0x squared. And 9 times 1, I've got 9x. Okay, I finished this diagonal. On to the next one. Negative 23, and I've got to do minus 1 minus 0. That's going to be negative 23 minus 1 minus 0 so that I can get up to the top. That's going to give me a total of negative 24, and remember it's the x squared diagonal. So I'm done with that diagonal. Okay, what times 6 gives me negative 24? That would be negative 4, and x squared to x squared, no extra x is needed. I've got the top, fill out the column, right? Fill out the column, make sure everything lines up. Negative 4 times 0 is 0x. Negative 4 times 1 is negative 4. Okay, now notice where we're at. We finished filling out, but we didn't finish going through all the diagonals. Remember, if you're going to have a remainder, it's because the whatever's left over is 1 power less than the thing you're dividing by. And notice it is. Look, I'm on the x diagonal, and I'm dividing by something with x squared. So technically, I'm now only just checking to make sure that everything adds up, because if it doesn't, I need to balance it out with a remainder like we did here, right? This didn't add up, the negative 15 with the negative 35. So I balanced it out with a remainder. But notice here we're all good. 9 plus 0 is 9x. Good. Negative 4 is negative 4. Good. What does that mean? We're done. Here's our answer. Here's the answer right here. Equals x squared plus 9x minus 4. Okay? So multiplication and division by the area method, if you practice it just a little bit, it'll start really sinking in, using the diagonals and figuring out all the things. It's kind of like playing one of those little puzzles either that the teacher gave you as a little kid, or those little books that they used to have you fill out with the question mark squares and things like that. It's always what it makes me feel like. So this method is just as powerful as long division. It will always work if you set it up properly. Make sure you don't miss any spots. Okay? And in my opinion, it's more organized. But you know, it's whatever works best for you. The long division or this method are comparable to each other. To finish up this lecture, this talk, let's take a look at the type of division that we'll be doing a lot of. It's very fast, it's very efficient, but the one drawback is that it can only work, the way we use it, it can only work on certain divisions. However, these certain divisions are the only ones that we'll be using a lot of, so this method is actually quite useful. Okay, so there is a more generic version of this type of division. If you're interested, send me an email. Someday I may have an extra video on that, but this particular division is called synthetic division. There is a way to have a higher form of it. It does require a little bit of practice. The form that we'll be using is very quick, very efficient, and it's the type of division that we run into 99% of the time for the applications that we use in these algebras. So you don't need to know the higher form. Okay? Here, synthetic division. A couple of key things before we begin. Okay? When you're doing synthetic division, the two things that are a must before you begin setting up the actual division itself is that the denominator must be linear. It must be x to the 1. And you really want the coefficient on the x to be 1. Okay? Now, if the exponent is not 1 in the denominator, you can't use this version of synthetic division. You would need the more powerful one. So I would recommend using one of the two methods that we just discussed. Okay? If it's not x to the 1 in the denominator, use one of the other two methods. If it's not 1 in this coefficient, there's a way to fix that, and I'll show you how that works when we're doing the last division here, okay? But notice this one right here, I made a specific point to showing you that we can't do this division with the synthetic that I'm going to show you here, and that's because the denominator has a square. The denominator is quadratic there. So we won't be using synthetic for that, okay? However, we're not going to really run into many of those divisions in this course. In fact, this will probably be the last one. Well, for the most part, 99% of the time. You won't run into those. Maybe when we're graphing rationals, you might run into a few, but really not many, okay? So, as long as you have both of these two things ready to go, then you're ready to set up the synthetic division, okay? So, what we have with synthetic division is what I call the box. What goes in the box is whatever causes the denominator to be 0. Okay? So notice what I'm about to put in the box here is positive 4. So I'm taking this, and this positive 4 is representing that x minus 4. Notice I didn't put any variables. Okay? And that's part of what's going to make this method very efficient. I won't be using variables at all, okay, except to express the answer. This number has to represent this whole binomial, and it does so by being the number that zeroes it out, okay? So we call this x minus 4 quote unquote a factor. If it divides evenly, it's a factor of this, but it by itself can be a factor by itself, okay? And 4 is the number associated with that factor. Now, next to the box has to be the numbers representing what you are dividing by. Again, make sure you're not skipping any powers. 2, 1, none, good to go. What I'm going to do is I put these coefficients, 1, 5, negative 36. Okay? Now, I'm almost done setting up. To finish setting up, you put a 0 underneath in the first column. You draw a line here. Okay? Now, of course, the line is immaterial, but all right, so whatever number's in the box is what I'm eventually going to be multiplying by to get my next columns. Okay? But here are the rules and the setup for the synthetic division. Anytime you have a completed or a semi-completed column, which means you have the top row and you have a number waiting underneath of it, that's a semi-completed column. You can complete the column by adding. Okay? So this is what you do. You add this way. Okay? So 1 plus 0 is 1. Once you have completed a column, like so, you use multiplication with the box to start the next column semi-completed. So 4 times 1, okay? 4 times 1 is 4. Okay, well now I have a semi-completed column again. So I add, that gives me 9, right? Now that I have a completed column, I multiply again to get the next column going. So from here to here, 4 times 9 is 36. I have a semi-completed column. I complete the column by adding, right? Negative 36 plus 36 is 0. Okay, now once you've hit the end, you can look at the numbers on the bottom, and basically you just need to be able to interpret the answer, okay? And here's how you do it. The last number is always the remainder. Remainder. From there, you always count up by powers. So this has to be the number, in other words, the none, no x's, and then I would count up to x. If I had more numbers, I would go x squared, x cubed, right? It would just keep counting up by x powers. right? So this is telling me that I have 1x plus 9 number. So this is telling me with 0 remainder that my answer is x plus 9. This is my answer to that division. Okay? Notice it's true. If I multiply x minus 4 times x plus 9, I will get x squared plus 5x minus 36. All right, let's do a couple of more synthetic divisions and then we'll hit that same one that we were doing earlier. So here we go. Here's the thing that I'm dividing. I'm going to set it up and then we're going to run through it and you'll see how quickly we can actually do these things very efficiently. So I'm looking at x minus 6, so I put a 6 in the box, right? X is to the 1, there's a 1 in front of the x, it's all good to go. I have 8, 5, 4, right? So negative 3. 5, 4, there's no 3 power. So I put a 0. 2 power would be 7. 1 power is negative 1, and then 2. Put a 0 underneath the first column, draw the line, and buckle up. Make sure you're with me at this point, right? I have 8, negative 3, no cube power, 7, negative 1, 2. Ready? Okay, here we go. 8 plus 0 is 8. 6 times 8 is 48. Negative 3 plus 48 is 45. 6 times 45 is 240 and 30 is 270. 0 plus 270 is 270. 6 times 270 is 1200 plus 420, so 1620. Plus 7. Here, let's get some columns in here because I'm getting a little bit off. That's 1627. All right, times 6, I've got 6,000, 9,600, 9,720, 9,720 plus 42. So 9,720, 42 is 62. Okay, minus 1 is 9,761. So times 6, I have, all right, let's do it in order here. 6, right? 36, 45, 58, right? Okay. So then plus 2, 5,800, 568, right? Okay, so now I just need to interpret the answer. So from here, I'll have remainder, right? This will be number, this will be x, x squared, x cubed, and x to the 4th. So I have my answer is 8x to the 4th plus 45x cubed plus 270x squared plus 1627x plus 9,761. And I actually have a remainder this time, right? So I have to put plus 58568 over the original divisor x minus 6. Okay? Now I put this example in here to show you that this was a division you definitely would not have wanted to do by long division or even that other chart. But notice synthetic division just knocks it right out. You just need to be able to multiply and add real quick, right? You don't even have to multiply and add real quick. You can even have a calculator by your side getting you through it real quick until you get more used to doing it, and then you probably end up having it yourself. Okay, so let's move on to another one. Right here, notice I have 1 and x to the 1, so this one's ready to go. The number that I put in the box is -5. Now let's take a second right here. Do you notice how the thing that makes the denominator 0 is always opposite in sign of the number, right? When I'm doing division, at every step, aren't I supposed to subtract? And I know what you're thinking. Wait, we add every time. Shouldn't I be subtracting? Well, that's the beauty of the multiplication by the box. Notice the box is the opposite sign. It has that subtraction built into it. That's another thing that just speeds this right up. The subtraction is already built in by doing this opposite sign here, okay? But also there's a connection with the fact that this number makes this denominator 0, okay? And it's not division by 0. There's something else with factoring that we're going to do in the next section. You'll see the reason why that's a good connection. Okay, so let's set up. I have 1 x to the 3, so 1. But there's no x2 or x to the 1. So I have 0, 0, and then the number 125, right? Put my 0, draw my line. Buckle up. 1 plus 0 is 1. -5 times 1 is -5. Add 0, -5. -5 times -5 is 25. Add. -5 times 25 is -125. Add, I get 0. And the division is now done. So I interpret. This is the remainder. This is the number, x, and x squared. So what's the answer? Right? This must be the x squared. This must be the x. This must be the number and the remainder, right? Okay. So then the answer to this division is 1x squared minus 5x plus 25. No remainder, so I don't bother putting anything after that. Okay? So this is meant to be that quick, right? If I went too fast, pause, go back, rewind, see it again. Feel free, okay? But that's about the speed that you're going to want to get used to. Practice, get used to doing these things. Practice it. Get used to doing those things that fast, because later on, when we're actually analyzing polynomials, you may have to do 4, 5, 6, 7 of these divisions in one problem. Okay, it might take that, but notice how quick they go. Right? These divisions are designed for a specific purpose, which is why they're only good at a certain structure of the division. Okay, there is a more generic form, but it's not as quick. It's kind of quick, but it's just not as quick. Okay, we only need it for this certain kind of division because this is the kind of division we're going to hit a lot. Now, the last one. The one that we already know the answer to, right? Okay. Can synthetic division do this one? Yes. Is it going to cause fractions? Yes. But fractions are life, right? I notice that I do have x to the 1, and that is exactly what I need to make sure that I can at least do this. However, we don't have the 1 coefficient, do we? So here's what we have to do. I'm going to have to divide by 2. But of course, in a big fraction like this, that's not legal unless I divide everything by 2. So that means this has to be divided by 2, this has to be divided by 2, divided by 2, divided by 2, divided by 2. Okay, so let's rewrite the division in this new format. It's going to be 3x cubed plus 37 over 2x squared plus 23x minus 15 over 2 divided by x plus 7 over 2. Now notice it's exactly what we need. I have a 1 x to the 1. Let's set up the synthetic division. I will put negative 7 over 2 in the box, right? Because that's the opposite of this. And then my coefficients, 3, 2, 1, none. I didn't skip any, so I can just go 3, 37 over 2, 23, and negative 15 over 2. Put my 0, draw my line, and buckle up, right? So 3 plus 0 is 3. Negative 7 over 2 times 3, well, it's 3 over 1. So I'm just doing the 7 times the 3, and it's negative. So negative 21 over 2 times 1 is 2. Look, they have the same denominator. Yes! 37 minus 21 is 16 over 2. Wait a minute. 16 over 2. That's 8. Boom. Negative 7 over 2 times 8 is 7 times 8 is 56. But divided by 2, right? That's going to be negative 28. If you do negative 7 over 2 times 8, you will get negative 28. Then 23 minus 28 is minus 5. Negative 7 over 2 times negative 5. Negative times negative is positive. 7 times 5 is 35 over 2. Notice they have the same denominator again. Always works good that way. Negative 15 plus 35 is 20 over 2. Uh-oh, that's 10, right? So I can simplify that to 10. All right, let's interpret this answer. I'm going to make some space so that we can write out the answer here. Let's make some space. So this is remainder. This is number x and x squared. Okay, so bear with me. The answer to this division, the fixed one, is the one that we just did. It's going to be 3x squared plus 8x minus 5. That's going to stay the same no matter what, even to the original problem. Okay? So that's actually the main part of my answer. It's the remainder I've got to fix. And the reason is because I technically changed my thing that I'm dividing a little bit, right? It's 10 over x plus 7 over 2. Okay, but I can fix that back to the way it was by just doing times 2 now. Times 2, times 2, times 2. It's the opposite of what we did over here, right? I divided everything by 2 to make it temporarily usable. Now, in the fraction portion, that's the only portion that needs fixing. The fraction portion, I'm just going to fix by remultiplying the 2 back in. And it's legal because I'm doing it to the top and the bottom. So I'm not actually changing the value here. It's technically correct. I'm just making it look more like what we're wanting. So the final answer is 3x squared plus 8x minus 5 plus 10 times 2 is 20. 2 times x. 7 over 2 times 2 is 7. So as you realize, that is now the actual answer that we got before. And we just had to finagle a little bit. More good news is, for the most part, we won't have to do that very much in the divisions to come. Most of them are going to be like these 3. Okay? So in the next several sections, you're going to get a lot of practice with synthetic division, because this is the one that's quick and efficient, and the one where we do a lot with our divisions that involve factoring. That is actually the main goal here. We are going to be using division for factoring. Okay? So I hope this brief section has given you enough insight and enough of a jump to decide what kind of division you like, and to give you a heads up of the synthetic that's to come.